All right, here we are, Calc 3, video 2. This guy is meant to be watched on tomorrow, Wednesday the 26th. I'm gonna make it less than 25 minutes long so that at 8:25 in the morning or 12:55 in the afternoon, depending on which class you're in, the video will end and we can talk about it. And for many of you, I know this is a review because we've talked about this before. So here we go. Let u be the vector u1 comma u2 u3, and let v be the vector v1 comma v2 comma v3, and these are in 3 space, so they're out in space somewhere. Let's just have 2 vectors here like this. Here's u and here's v. Okay? And so there's an angle between them, and this angle theta is the cosine inverse of u dotted with v over the norm of u times the norm of v. And so what is this dot product? All right, so definition. U dot v, we don't say u multiplied by v because you can't multiply 2 vectors, but you can compute their dot product. And this is just, you take u1 times v1 and add it to u2 times v2 plus u3 times v3. So you multiply the components u1 v1 plus u2 v2 plus u3 v3, and you get a scalar, which is just a number, right? 5 or something, okay? Now, note, if theta is pi over 2, in other words, if this is the right angle, right, then this number inside the parentheses here equals 0. Right? Because the cosine of pi over 2 is 0. Okay? But these lengths can't be 0 because we wouldn't have a vector. So the denominator here is non-zero. So this says, well, that what? That u dotted with v equals 0. Okay? So what does this say? This says, all right, this is a little theorem here. If I have 2 vectors, u and v, and their dot product equals 0, then u and v are perpendicular. And in our language, vector language, we say they're orthogonal. And the dot product is a scalar. It's funny because when you take the dot product of something, it doesn't really tell you anything unless it's 0. Otherwise, it's just the number you use to get in here and find this angle, whatever it might be, okay? And so the properties of the dot product. All right. So 1 u dot v equals v dot u, associative. 2, if I have some constant k and I multiply it by the vector u and then dot that with v, that's the same as k times the dot product of u dotted with v. Right? And it distributes over sums. So u dotted with v plus w equals uv, u dot v plus u dot w. Let me make sure I got all this right. uv equals vu, kuv is k uv, u dot v plus u is u please. Okay, and the last one is that if you take the dot product of a vector with itself, this is the same as the length of the vector squared. Okay. And that's about all I have to say about the dot product. Maybe we should do an example here. Here's a good quiz question here. Example. Are the vectors u equaling 1, 2, minus 1, 1, 2, minus 1, and v equaling minus 1, 0, 2, are u and v orthogonal? In other words, are they right angles to each other? So here we go. We compute u dot v, and we get 1 times minus 1 plus 2 times 0 plus minus 1 times 2. What's that? Minus 1 minus 2, it's minus 3. It's not equal to 0, so they're not orthogonal. Okay. And key, very important, a dot product of two vectors is a scalar. All right. So now let's talk about the cross product, which is a little deeper and more interesting. Okay. If we have two vectors u and v, and if u is not parallel to v, then u and v determine a plane. And let's just keep working in R3 here, right? It could be in R2. That could actually be in R4, but we'll never work in R4. So here I've got my vector u down here. And here I have my vector v over here. And sure enough, on this piece of paper, u and v determine the plane that makes this piece of paper, okay? Now, this has to go in order, so order is important. If I take u cross v, right, then by the right-hand rule, u goes towards v, this angle theta, and this cross product gives me a vector, which I'm going to call n, right? So two vectors, when you cross them, gives you another vector n, and this thing is orthogonal to both u and v, okay? So there's a right angle with n and v and a right angle with n and u, and because u is going towards v, and my fingers, if I curl them in the same direction as theta, the thumb goes up, and that means the n is in the upward direction. Okay? And so u cross v gives us a vector, which turns out to be the norm of u times the norm of v times the sine of theta times n. And this little n here it's a unit vector, so it has length 1. Okay? And u cross v is a scalar multiple of n, right? Depending on how big u cross v is. Right? And here's a note. Am I still on the page? Yep, note. If u cross v equals 0, then u is parallel to v. All right, so now we define the cross product. Cross products continued. Note, I'll make this a note here. U cross V is not equal to V cross U. Okay. Because of the right-hand rule, right? V cross U is going to have take this picture back here. So V cross U is going to go in this direction. And so by the right-hand rule, that thing's going to go down. So it's going to give you a vector going. I can't get my hand upside. Well, here we go. If you go upside down with the hand, the fingers are going this way, and the thumb goes down. So this N is going to be in the negative direction, or the downward direction from whatever the other one is. Okay. However, U cross V is equal to minus V cross U. It just changes the direction. Okay, so let's get the axes up here. I'm going to make a big picture here, so we have lots to work with here. And tie together some of the stuff we did in the earlier sections here. This is Y, this is X, and this is Z. Remember the standard unit vector, so I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. These are all vectors, right? So I got some colors here to play with. So here's the vector I. It lies on the x-axis. Right here, and it has length 1. Right? Here's the vector. Oh, I got some colors here, some blue. Here's the vector J. It's not going to show up very well, but there it is, the vector J. That guy lies on the y-axis. And then I've got green here, and this is going to be vector K. And that lies on the z-axis. So okay, if we take I cross J, just like we did before, so this means the theta I'm using is opening that way. I cross J equals K by the cross product. And similarly, if I take K cross I, so let's see here, K cross I get J. And if I take J cross K, I get I. And we can use all these to figure out how to find the cross product of two vectors in 3 space. All right, doing good on time here. So properties of the cross product. One, if I have scalars R and S, and I take RU cross SV, this turns out to be RS times U cross V. So 2. If I take U cross the sum of the vectors V plus W, this is U cross V plus U cross W. Three is the one I had before. U cross V is equal to minus V cross U. And lastly, if I take the 0 vector and cross it with u, I get the 0 vector. Okay. So, how do we compute the cross product here? Because that's what we want to be able to do, right, is do some computations. Computing u cross v. Every semester, someone finds a different way to do this from a physics class or an engineering textbook. You can use whatever you want as long as you're comfortable with it and it works. Like I said, there's lots of ways to do it. I use a matrix. Okay, and so again, if u is the vector u1, u2, u3, and v is the vector v1, v2, v3, then u cross v, here's what you do. You set up the determinant of a matrix and you put the I and the j and the k here. And these are the standard normal vectors. And since it's u cross v, the first row is going to be u1, u2, u3. And the second row is going to be v1, v2, v3. And these straight bars say you compute the determinant, which is just you take I times the determinant of u2, u3, v2, v3, minus j times u1, u3, v1, v3, oops, that should be v1, v3, plus k. So u1, u2, v1, v2. Add all these together and you get a vector. Okay. And so, all right, let's do an example. So let u be the vector 1, minus 2, 1, and v is the vector minus 2, 3, minus 1. And so u cross v is going to be I, j, k, 1, minus 2, 1, minus 2, 3, minus 1. These are vectors. So it's I times the determinant of this thing, so minus 2, 1, 3, minus 1, minus j, 1, 1, minus 2, minus 1, plus k, 1, minus 2, minus 2, 3. And let me pause here and make sure I haven't made any errors. 1, minus 2, 1, 3, minus 1, minus 2, 1. 1, 1, minus 2, minus 1, 1, minus 2, minus 2, 3. Okay. And so this becomes I times, what is this? So you take this number, which is 2, minus this number, which is 3. Again, minus j times this number, which is minus 1, minus this number, which is negative 2, plus k times 3 minus 4. 3 minus 4. Okay. And you wind up with minus I, minus j, minus k. And that's the cross product of u cross v. Now, what am I at? 19 minutes. We're perfect today. Like I said, as the semester wears on, I'll get better and better and better at my timing. 3. Cross products. So let's say you computed this u cross v, and you got that u cross v. I'm just rewriting what I have on the other page here. Minus I minus j minus k. What's v cross u? Well, it's the minus of u cross v, and that's I plus j plus k. Okay, the last piece here, this is just sort of an application part. It's a pretty cool result that if you take two vectors, u and v, you take the cross product and you take the length of it. This is the length of u times the length of v times the sine of theta, where theta is the angle between. Theta is angle between u and v. But this number here also equals the area of parallelogram formed by u and v. So here we go. Here's v, and here's u. All right, here's the vector u. Here's the vector v, and there's theta. Okay. If I make this into a parallelogram here, so if I transpose v to here and u up to here, and this is angle theta, the area of this guy just equals the norm of u cross v. And when we get to talk tomorrow, I'll really flesh this out and show you where that comes from. All right, so I'm going to stop there.